For nearly a century, we believed we had cracked the cosmic code. We thought we understood the fundamental blueprint of the universe, from the first moments of the Big Bang to the swirling gases, the first stars, and finally, the majestic galaxies that populate the cosmos today. It was a slow, majestic, and orderly evolution governed by predictable physics. But then, humanity pointed its most powerful eye, the James Webb Space Telescope, JWST, deeper into the cosmos than ever before. We looked back in time toward the very dawn of creation and saw something impossible. JWST detected a population of galaxies that are massive, fully formed, and blazing with light. The profound problem? They appear to have reached cosmic maturity before the universe's own timeline should have allowed it. They are defying 13.8 billion years of established cosmic law. Meet HD1, Z8_GND5296, and a handful of other ancient giants. They are the rogue fossils of a forgotten era, forcing a complete rewrite of the cosmological story. This is the profound mystery of the galaxies that defy cosmic law. The galaxies that shouldn't exist, but dazzlingly, brilliantly do. The standard model, building a universe. To appreciate the scale of this problem, we must first establish the accepted timescale. The lambda cold dark matter, or lambda CDM, model. Our universe begins 13.8 billion years ago. For the first 380,000 years, it was an opaque, superheated plasma fog, the cosmic dark ages. Light couldn't travel freely. When the universe cooled enough, hydrogen and helium atoms finally formed, releasing the light we see today as the cosmic microwave background, CMB. This is our earliest baby picture of the universe. The CMB is incredibly smooth, meaning matter was distributed nearly uniformly. Over the next 100 to 200 million years, gravity, aided primarily by dark matter, began to amplify tiny density fluctuations. This created the gravitational scaffolding for the first structures. First, the gargantuan, short-lived population 3 stars ignited, made only of the primordial hydrogen and helium. Their explosive deaths seeded the cosmos with the first heavy elements. Only then, the lambda CDM model predicts, could the first true galaxies begin to coalesce. Small, dim, and slowly merging over billions of years to reach the size of the Milky Way. This model predicts a gradual, hierarchical growth. Small structures form first, then merge into larger ones. This process takes time, lots of time. The discovery of the cosmic ladder. Before we examine the impossible galaxies, let's talk about how we know how old they are. To look back in time, astronomers rely on the cosmic distance ladder. The final crucial rung of this ladder is redshift. In the 1920s, astronomer Edwin Hubble observed that the light from nearly every distant galaxy was shifted toward the red end of the spectrum. This wasn't a Doppler shift from movement through space, but rather the light being stretched by the relentless expansion of space itself. Hubble established that the farther away a galaxy is, the faster it appears to move away from us. This is Hubble's law. The higher the redshift, the deeper we are looking into the past, toward the Big Bang. The light from the oldest galaxies has been stretched so severely, it shifts completely out of the visible spectrum and into the infrared. This is why JWST is revolutionary. Hubble could only glimpse these earliest epochs. JWST, built specifically to see that stretched infrared light, is essentially peering through the cosmic keyhole, straight back to the cosmic dawn. The earliest JWST objects, those with the highest redshifts, are light that traveled for over 13 billion years. They are snapshots of the universe when it was barely 330 million years old. Enter the impossible galaxies. The first sign of trouble came from the Hubble Space Telescope, with objects like Z8_GND_5296. Discovered a decade ago, this galaxy existed when the universe was only 700 million years old. It was already massive, forming stars at a rate 150 times faster than the Milky Way. This speed was already challenging, but the mass was the true riddle. There hadn't been enough time for gravity to gather that much matter. Then came the flood of data from JWST. In 2022 and 2023, JWST detected a vast population of galaxies, some existing when the universe was just 500 million years old, that were surprisingly luminous, structured, and heavy. They were already disk galaxies, spirals, and large ellipticals. The Lambda CDM model predicted that at that age, 99% of galaxies should be small, dim, and shapeless dwarfs. Instead, we found monoliths. The size and mass of these galaxies implied that they must have assembled their stellar components, the baryonic matter, at an unprecedented, hyper-efficient rate, essentially forming billions of stars in the time our models expected them to be gathering gas. This conflict has forced a critical, painful reconsideration of the foundational physics of our universe. The physics of dark matter and the crisis. The reason these galaxies pose a crisis lies in the physics of cold dark matter, CDM. CDM is the dominant component of mass in our model, acting as the gravitational scaffolding for all structures. The term cold means its particles move slowly, allowing gravity to easily pull them together into dense clumps called dark matter halos. Lambda CDM simulations predicted how quickly these halos could form and merge. The maximum size of a halo at 500 million years was thought to be modest. The James Webb Space Telescope discoveries reveal that the largest halos must have formed and grown exponentially faster than predicted. This problem is a counterpoint to a long-standing issue in cosmology, the missing satellite problem, where Lambda CDM predicts far more small dwarf galaxies than we actually see. Now JWST presents the too big too soon problem. The largest, earliest galaxies are also overabundant. The model is failing on both ends of the cosmic scale. Too many small things in theory, and too many large things in reality. To solve this, cosmologists must tamper with the dark sector. Perhaps dark matter isn't cold, but warm, meaning its particles move faster and suppress the formation of small halos, while allowing the larger ones to grow. Or perhaps the missing ingredient is a hypothetical early force. The existence of these massive structures suggests that the seeds of gravity were simply more effective than we ever gave them credit for. The theories: shortcuts to maturity. If the Lambda CDM timeline is too slow, what are the cosmic shortcuts these galaxies used? 1. Hyper-efficient star formation. The simplest solution: the first galaxies were just unbelievably effective at turning gas into stars. They used gas clouds that were pure and cold, metal-free. This gas collapses faster and more efficiently than the metal-enriched gas in modern galaxies, leading to a frantic, explosive period of star formation that rapidly assembled mass. This would explain the blinding UV light we see from HD1. 2. The direct collapse black hole mechanism. This focuses on the immense energy required. The brightness of objects like HD1 suggests an engine far more powerful than just star formation, an actively feeding supermassive black hole, SMBH. But how could an SMBH of 1 million solar masses form so early? The direct collapse theory proposes that in the early universe, vast clouds of gas, prevented from cooling and forming normal stars, simply collapsed directly under gravity into a massive seed black hole. This shortcut skips the stellar death and growth phase, allowing the SMBH to form instantly and begin fueling the galaxy's extreme luminosity. 3. Early dark energy, or modified gravity. The most radical solutions involve changing the rules. A new hypothesis suggests a short-lived phase of early dark energy right after the Big Bang. This temporary anti-gravitational force would have temporarily accelerated the expansion of the universe, but crucially, it would have also created more gravitational seeds for dark matter to condense around. This could simultaneously solve the too big too soon problem and the famous Hubble tension, the mismatch in the universe's expansion rate, offering a single fix for two major crises. The challenges of the deep cosmos. It's crucial to understand the heroic difficulty of these observations. These galaxies are the faintest objects ever detected. Their light has been stretched and attenuated across 13 billion light-years of expanding space. When astronomers say these galaxies are massive, they are making a calculation based on the total light observed, the color of that light, and its redshift. This process is fraught with technical challenges. Dust obscuration. Even tiny amounts of early cosmic dust can block light, making a truly huge galaxy look dim and forcing us to underestimate its size. Contamination. A foreground galaxy or star can sometimes blend with a background object, skewing the redshift and mass estimates. The power of lensing. Unseen gravitational lenses can magnify the light of a distant galaxy, making a small object appear far more luminous and massive than it truly is. While astronomers are rigorously applying correction factors and multiple confirmation checks, which is why the crisis persists, every single data point from the early universe is hard-won and carries significant uncertainty. The truth may lie in a combination of factors. Perhaps the galaxies are 90% as massive as estimated, but the star formation was 10 times more efficient than predicted. The ongoing work is not just measuring light, it's recalibrating the fundamental physics of the universe's infancy. The universe rewritten. The discovery of the impossible galaxies like HD1 and Z8 _GND _5296 marks the end of an era in cosmology. The Lambda CDM model, our cornerstone for decades, is buckling under the weight of these early, mature giants. They shouldn't exist according to our most trusted equations, but they do. And because they exist, we must accept that the universe grew up faster than we thought. Whether the cause is a tweak to dark matter, a shortcut in black hole formation, or a completely new force like early dark energy, the story is being rewritten. Every time we point a better telescope at the sky, the universe answers, with a riddle that forces us to be humbler and smarter. These galaxies are the ultimate reminder that the greatest discoveries often lie at the edge of what we believe to be possible. If this deep dive into impossible galaxies lit up your curiosity, hit like, share this video, and subscribe to Cosmic Crunch, where we turn the weirdest corners of the universe into wonder. Drop a comment. What do you think? Did these galaxies form faster? Or is something deeper rewriting the laws of physics?